Hi, so I'm from Duke University, and I'm here to present my work. It's titled Better Performance Through Threadlocal Emulation. This is ongoing work, and I'm doing this together with Valentin Pistel, Alex Meyer, and Landon Cox. So we have a goal. We want to track how apps use data. And I want to motivate this goal with a very simple example. So consider the Instagram app. Oh, wow, the pictures are bad. Okay, consider the Instagram app that I'm using on my phone. So with Instagram, I can browse the pictures that others have posted, or I can take pictures and post it so that my friends can view them. So Instagram has access to my camera. Notice, however, that I have no real idea what Instagram is doing with the camera. How do I know that Instagram is not creating multiple copies of my picture in my file system and thereby wasting space? So I really want to know what Instagram does when Instagram saves a picture taken from the camera onto my file system. And I can do this with dynamic taint tracking. And here's how I would do that. So the first thing I would do is mark the camera as a taint source. This tells the tracking system that anything that comes from the camera should be tracked. So when the app actually runs that line of code, the tracking system is going to mark that variable as tainted. Next, when the app makes use of this variable to modify the picture and to make new copies and stores the results in new variables, the new variables themselves are going to be tainted. And this is a result of taint propagation rules, which specify how taints are moved from one variable to another. Finally, the app would try to write the file at some point of its execution. And since my goal here is to log an event each time a photo is saved as a file, I would mark the file system as a taint sink. Anytime tainted data reaches a taint sink, I can run some custom action. And in this case, it's just logging that action happened. Dynamic taint tracking has been around for a really long time. So a decade ago, security folks were looking at it from a perspective of malicious apps. How do we detect apps that harvest all the personal data on my system and try to defeat them? In the continuing years, however, there has been a lot of work in using taint tracking in different contexts because it has shown itself to be a highly versatile technique. So it is beyond the scope of this talk to talk about all these different systems and how they use taint tracking. And I encourage you to read the paper if you're interested. But I am going to focus on one paper that came out from our lab in 2011, and it's the UProof project. Let's go back to Instagram. So the picture's really bad, so I'm just going to describe it in words. Suppose I come across a picture that has two swans, one white and black, and in the middle there's a sign that says, "Do not feed swans." So I'm looking at this image and I'm wondering to myself, how do I know that maybe if the swan was really there? People go through great lengths to create the perfect Instagram selfie or picture. Perhaps someone digitally altered this picture and then uploaded it online. So, could I really know that, this image is authentic? And UProof tries to solve this problem. And the way it does so is by allowing whoever who uploaded the picture to also upload a proof, proving that the image is authentic. And one of the building blocks in UProof is taint tracking. And let's see how it uses taint tracking. So this is the same code snippet as before. Nothing has changed, except that the goal is different. We want to prove that the camera images are authentic. The first thing UProof does is mark the camera as a taint source and the file system as a taint sink, just like before. Next, when the app tries to take a picture, UProof detects that the picture is being taken, and it will transparently create a copy of the picture, mark it as the original, and keep it somewhere safe. Next, the taint tracking system will take over and taint that variable and let the app run normally as usual. So the app is going to run, it's going to do all its things, taints are going to be propagated, and finally at some point the app is going to save the file, save the image as a file. At this point, since the file system is a taint sink, UProof is going to run a custom action. And in this step, it's going to take the new picture that the app saved, the original that it had a copy of, and compare them together. And the output of this comparison is going to serve as a proof. It's called the authenticity certificate, and it's something that's going to be uploaded together with the picture so that whoever's viewing the picture can know whether the image is authentic or not. So in this case, that certificate is represented as a heat map where the cold regions are parts of the picture that are not modified, they are true, and the red region, in this case the white swan, was actually digitally added in. So taint tracking is crucial in uProof because it allows us to match the output of the app, in this case the new image, with the input that caused that output, which is the original image. uProof uses Taint Droid, which is implementation of dynamic taint tracking on Android. Taint Droid is implemented within the Dalvik virtual machine, which is which is a managed runtime, much like the Java virtual machine. It has reasonably good performance. It only adds an overhead of about 14%. And this is because if you run apps on a VM, it's slow to begin with. So, and adding a little bit of taint tracking logic does not really hurt us much. On modern mobile platforms, however, we see a trend towards native code. For example, starting from Android 5 and above, the Dalvik VM is no longer used to execute apps. Instead, when an app is installed on your phone, it is compiled to native code so that it runs on the CPU directly. And this is done for performance reasons. And this the performance reason is also motivating developers to actually include native libraries in their app. So they might write most of their app in Java, but if they're doing specialized tasks like computer vision or speech recognition, then they might rely on native libraries provided by the OpenCV and the CMU Sphinx project. All this means if you want to do native taint tracking on modern mobile platforms, I mean, if you want to do taint tracking on modern mobile platforms, you want to think about taint tracking native code. Unfortunately, as previous work has shown, tracking native code is expensive. The slowdown might be at least 10 to 30 times. We consider this unacceptable because we want to build a system that runs on real devices with real apps, and you want really good performance. So how do we do better? Let's go back to our Instagram example. So here I was only interested in tracking how the camera is used. So there's an intuition there that if I want to track how the camera is used, then I only need to do so when the camera is actually used. Otherwise, if I'm just browsing pictures on Instagram, then I should not run taint propagation, do any taint tracking and incur the overhead of doing so. So the key insight is you take the overhead that hopefully happens in limited portions of the app's runtime and amortize it over the app's entire lifetime. This is not our idea. It was proposed in a different context by the Zen team. And the way they did this was by using page protections. So you use page protections to prevent reads and writes to tainted data in memory and let the app run unmodified. When the app eventually tries to access tainted data in memory, you trap the fault from the kernel and you begin emulating the app. So you disassemble the app's instructions, perform taint propagation based on the semantics of the instruction, execute it, and then loop until the app no longer uses tainted data. We cannot use this directly in a mobile context because mobile apps are inherently multi-threaded. So consider an app with 4 threads, 1 UI thread and 3 worker threads. They're all running normally, and at some point, the 3rd thread decides, I want to take a picture of the camera. When this happens, and if you only rely on page protections, you're going to have to emulate every single app, and they're all going to run slowly. Notice that this is a waste because only worker thread 2 is handling tainted data, which means you only want, what you really want is something like this. You have the same 4 threads, they run normally as per usual, and when worker thread 2 tries to access tainted data, that will be the only thread that is emulated. The other threads will run normally unmodified. And eventually, when worker thread 2 itself stops handling tainted data, it will resume normal execution and run at regular speeds. We call this property Threadlocal emulation, which states only the threads handling tainted data are emulated to perform taint propagation. Otherwise, they run at regular speeds with little overhead. In our work, we are interested in implementing Threadlocal emulation to build a dynamic taint tracking system for the new versions of Android. And there are many implementation challenges. But one key question is, how do we interpose on memory accesses on a thread level basis? So let's focus on this a little bit more. So here's a different view of the same example. On the left, you have the same 4 threads, and on the right, you have a memory layout where memory is organized in terms of pages. That gray, well, it's black here. That black box there represents a protected page where reads and writes are denied. And that red section there represents tainted data in that protected page. Okay, so when threads access untainted data, the app is just going to execute normally without any problems. But when one of them accesses tainted data, we want to emulate that thread. But herein lies a conundrum. How does the emulator access that tainted data in protected page? So one strawman approach would be to say, well, let's just remove page protections. But see, the unfortunate thing here is that you have all these unemulated threads that may now access tainted data without page protections preventing them, and they themselves will not be emulated. And because they're not emulated, we can't perform taint propagation for those threads. So the next thing we can say is, well, let's just emulate everything so that we'll always perform taint propagation when necessary. But this is precisely what we want to go away from. We want thread local emulation. So how do we implement this? One way would be to play around with the page table itself. So here I have also included a view of the physical memory in addition to the virtual memory that the app sees. So each page in the virtual memory table maps to an individual physical page. So let's see how this will work. When worker thread 2 tries to access tainted data, we might emulate it. I mean, we will emulate it. And the next thing we will do is create a new entry in the virtual memory table that maps to the same physical page that contains the tainted data. Next, the emulator is going to use this new page to access tainted data instead of going through the protected page. This is one approach, it's a software approach. One might argue that it's not very robust because now you have all these other threads that can also access tainted data through this new entry in the virtual memory. There are alternative approaches, so you could rely on hardware techniques, features available in the hardware platform, like virtualization features, to have a more robust memory protection scheme. In our current prototype, we make use of memory domains, which is a feature available on the 32-bit version of the ARM CPU. And the memory domains allows you to, in addition to page protections, allows you to have a different kind of a memory protection scheme. So for more details, please read the paper, or we can have a discussion offline. So far, I've been discussing about thread local emulation in terms of implementation. But we've also thought about this from a higher level perspective, which is, is it going to be useful all the time? Is it going to deliver the performance that we need? And I'm going to present here a limitation that we came up with. So on the left is a picture of me trying to take a picture of working on my slides. And on the right is what you see in Instagram as soon as you take a picture. You can apply a filter to make the image more attractive. So notice that in my previous examples, I've been using the camera as a taint source. Therefore, anything that comes out of the camera should be tainted and tracked. Now, this means that we technically have tainted data on the UI thread because the UI element is showing a preview image of whatever that my camera captured. Does this mean we are going to have to emulate the UI thread now? Will this not prove to be really slow? So unfortunately, I don't have answers for you right now because our prototype does not run real apps yet. But I assure you, it's not a fundamental limitation. We just have to get a lot of work done. But we'll get there in a month. And then we'll have answers for you in a month. So to conclude, hopefully I've convinced you that dynamic taint tracking is useful. We should think about it more than just about malicious apps. There are all these other cases where it might be useful. And if you want to do taint tracking on modern mobile platforms, we need to start thinking about doing native code taint tracking. And our position is that for really good performance, you require thread local emulation. There are plenty of research and implementation questions left. I'm sure you have a lot of them. So ask the simple ones now and the hard ones later. Thank you.